Build software without a plan, and you guarantee massive, costly rework. Spend too much time planning, and you delay time to market until the product is irrelevant. This tension exists because of a theoretical barrier known as bounded rationality. When dealing with complex software systems, engineers are restricted by hard limits in time, budget, and domain knowledge. Designing a mathematically optimal architecture under these conditions is impossible. Instead of chasing perfection, an architect's actual objective is to find a design that satisfies. To satisfice means to create a structural design that is demonstrably good enough. It satisfies the core requirements and sufficiently mitigates critical business and technical risks. Architecture serves as a calculable structural risk mitigation strategy. We can quantify this risk mitigation. Software engineer Barry Boehm analyzed the empirical relationship between development time, architecture planning, and the inevitable cost of rework. This chart maps the total project schedule against architecture effort and rework cost. As the time invested in upfront planning increases, the volume of rework reliably decreases. Because planning also consumes time, the total project schedule forms a curve. The lowest point on this curve is the design sweet spot, the exact ratio of planning where the cost of rework is minimized, producing the shortest possible project duration. For a small codebase, this sweet spot sits at just 5% of the total schedule. But for larger systems with millions of lines of code, the necessary architecture planning shifts to 37% of the timeline. When teams attempt to build massive systems using a lightweight 5% planning model, the result is violent design thrashing and continuous, expensive rewrites. Hitting this mathematical sweet spot requires stepping away from feature-driven roadmaps. The focus must shift to identifying and engineering architecturally significant requirements. Most standard features requested by users, like a button to view calculation history, do little to shape the foundation of a system. They operate entirely on the surface. The deep structures that hold a system together are dictated by architecturally significant requirements, or ASRs. This flowchart illustrates the pipeline from vague needs to concrete parameters. Stakeholders have business goals, generating ASRs, which determine the architectural structures we build. The first category is a constraint. These are non-negotiable rules, like a hard deadline or a mandatory programming language. The remaining drivers are quality attributes, the operational expectations like scalability, availability, and performance, and influential functional requirements, which are high-risk features known as architecture killers. If a requirement does not severely limit design options or mandate a specific structural choice, it is not architectural. It belongs in the product backlog. Stakeholders frequently present their needs using vague language, stating a system must be fast or highly reliable. Designing a system around these ambiguous terms introduces massive risk. This wheel illustrates the formal framework required to make attributes testable before coding begins. It locks down 6 variables: the stimulus, source, artifact, response, measure, and environment context. Consider a project tasked with building a simulation testbed for military combat systems, connecting disparate bases across the globe to run synchronized wargames. Formalizing the framework, we map the first 3 components. The source is the simulation generator. The stimulus is fake aircraft data. The context is peak wargame load. Next, we map the system's reaction. The artifact is the networked testbed. The response is a simultaneous sync. The measure is the exact latency window permitted before an aircraft appears to vanish from the sky. By quantifying that response measure, the engineers calculated the required data transfer rates and uncovered a fatal flaw. The data had to travel faster than the speed of light to hit the synchronization window. The math proved that the requested architecture violated the laws of physics. Formalizing quality attributes forces exact constraints into the open, exposing impossible requirements long before a single line of code is written. Once a scenario is formalized, measurable, and physically possible, how do we physically build it? Architecture is instantiated through 3 structures, acting as lenses on the same system. The module structure defines the static design time environment, classes, packages, and dependencies. The component and connector structure governs the living runtime environment, where active processes, data pipes, and APIs interact. Finally, the allocation structure maps the software to the real world, dictating where the code physically executes, from Docker containers to server racks. Arranging these structures is a constant exercise in compromise. Choosing to promote one quality attribute inherently degrades another. Designing the runtime structure for high availability by duplicating databases will simultaneously drive up infrastructure costs and degrade system simplicity. Architecture is the active, calculated management of these structural trade-offs across all three layers. This leads to the final operational question. In an agile environment, at what exact point do you halt upfront design and allow the engineers to write the code? This graphic maps the two states of architectural management: active design and passive design. Active design drives the process. It uses tight, iterative cycles to explore solutions, make tangible models, and evaluate tests specifically to hunt down and reduce structural risks. Passive design is the monitoring state. Once the system is live, the architect observes the codebase to correct architectural erosion, the gradual accumulation of technical debt, and chaotic dependencies that weigh a system down. The threshold between these states is exact. You stop upfront active design the moment the architecture is no longer the highest source of technical risk in the project. Reaching that threshold requires a strict sequence of logic. You map human stakeholders to their business goals, distill those goals into architecturally significant requirements, formalize those requirements into 6-part scenarios, and resolve the trade-offs across the module, runtime, and allocation layers. Software architecture is the rigorous discipline of translating human ambiguity into structural rigidity, securing the foundation until a system is safe enough